Hello everybody. We shall start discussing about our first astrophysical object today, the stars. Now, before we go to the discussion to the stars, we need to look at a few tools, one important tool particularly, which astronomers use a lot. So this tool is called correlation. And to deal with any two objects, the correlation of any two objects, let's ask the question, what do I mean if I say that two objects are correlated? Now, what can be these such two objects? Imagine a very hypothetical movie experience where we go to a different planet and we meet the aliens, and somehow we measure the height and the age of the aliens. Height and age. So say there are say 10,000 aliens for whom we have measured the height and the age. And then what I do, I just want to know some physics of them. Physics means what are the laws that governs the aliens. You can imagine that these aliens are going to be replaced by the stars very soon. But in any such cases where we can measure two or more quantities, what we do is that we plot one against the other. So say I plot the age against the height. Age goes from say 0 to 100 and height goes in some units, which also starts from 0, of course. And I see that all the data points that I get lies in this band. Okay, all the data points lies in this band. So this is a band which defines all the data points. It might have also happened, let's say this is not height and age that we are measuring. We are rather measuring the height and color of the dress. And I don't know how to quantify the colors, but imagine that for the colors also there is an axis. You can imagine it's a frequency of that color that we are plotting here, and again height. Now here I don't see a band like this. The data lies everywhere. If I would have done the same thing for human beings, so say human beings, let me draw with this color. Here it would have looked the same, because we know with age the height increases and after some time it does not increase much. On the other hand, for the height and color plot, we would have seen something interesting. What happens for the human being is that height remains constant after a certain age, but the people who are having higher age, our custom is such that we usually don't use many of the colors. We concentrate on certain colors, certain light colors only. So as the height increases, you expect that say the light colors will be more, and if the for the lower height where there are younger people, the colors will be more diverse. So here it will lie in a band like this. Okay, so I'm not drawing the individual data points because they'll mix up with the other one, but it will lie like this. So once I have seen these plots, what do I understand? So I understand here that height and color of dress are not correlated. So if it is correlated, then after this plot, If I tell you any point here and the age, you can tell me what is the range of height that age people will be. But if it is for the aliens, the height and the uh, color of the clothes are are not correlated, right? You cannot. So it can have any. If I tell you a color, it can be worn by aliens of any height. Here, height and age is correlated. Okay, so these correlation plots gives you a lot of information or understanding about these different variables. If one depends on the other, or something is there which is driving both of them. Both can be the case, right? Now it turns out that these are the things which you use a lot of times in astronomy. So I request you to look at correlation coefficients of different types. We will not discuss it in during the lectures, but this is something that you should look at. So that's all right. Let us come back to the stars. Back to the stars. For stars, we said that the total luminosity, we also call it bolometric. This is given by 4 pi sigma, all are constant. Sigma is the Stephen's constant, r square, and then t to the 4. So this is radius of the star. And this let us call effective temperature, For the time being, we can assume it to be a black body, so the effective temperature is the temperature of the surface of the star. Alright, so this is what we saw. And what else did we saw last time in our lecture on photometry? We said that we can measure the V band magnitude. We can convert it to the absolute V band magnitude, given that we know the distance to the star. Absolute magnitude is then V band. And then we can convert it to the bolometric absolute magnitude if we know the bolometric correction in the V band, and that will give me L. And we saw how to do UVB photometry to get to the luminosity like this. We also said that we can know B minus C color, and that will give us the effective temperature of the star. And to know the V minus C color, we have to do correction for the dust, etc., which we discussed in an earlier lecture. All right. So there are two quantities that we can know now. So we can have an idea of L and T effective. Even in the worst case, so this is if we know distance d to the star. If we do not know the distance, then what will happen? So I only know mv, which is minus 2.5 log 10 of L by 4 pi d square, and then you will have a C. So this will be minus 2.5 log 10 of L plus CV plus some constant which depends on D, some number which depends on the distance to the star, log of 2.5 log 10 of 4 pi d square. Right? So in this case, though I do not know the the exact luminosity of the star, but still I will be able to know the luminosity with respect to different stars, or the relative luminosity of different stars, if all those stars are at the same distance away. So for a cluster, we will know the relative luminosity. Okay, so we have some idea about the luminosity of the star, be it in a different unit, in some relative unit, and the temperature, effective temperature of the star. So there are two ways of looking at things now. So at worst case, we know the V band magnitude and the V minus C color. I'm sorry, not B minus C. I have been writing B minus C. It's B minus V. Let me correct that. Okay. So B minus V color gives you the effective temperature, and MV gives you the relative uh, luminosity. Now, with these two, I can do a correlation plot, or sometimes these are also called scatter plot because the points can be completely scattered in the plot. What would I expect if I do a scatter plot of L and T to the 4? So let us ask that question. Scatter plot L and T to the 4, and L and T rather, L and T. Okay. So L is 4 pi sigma r square T to the 4. So if all the stars, so I have a sample of stars, and let us say we are looking at a star cluster. Now, why I say that we are looking at a star cluster? There are two reasons. One I will tell you now, and the other I will come back to later. One is that this FD will be same for all the stars in the cluster. So if I plot MV, then all the stars will be off by a certain number. Or if I plot MV is essentially gives you the ratio of the luminosity of those stars with respect to certain luminosity. So that will be all off by a certain number, so that I don't bother basically. So this, let's say LV here, we can get to remember that MV to the volumetric magnitude, there is a volumetric correction, which is again will be same for all the stars. Now, if all the stars have the same radius, then log of L by some, it's better to weigh it with respect to some known luminosity. So we always weigh it with respect to the solar luminosity. So this turns for solar, and this will be some constant which is depending on 4 pi sigma r square, and then log of T by T sun, this plus 4 times log of T by T sun. Why? Because again, it's log of something to the power 4 is 4 times log of that. So if I plot these two, so remember that this is only for this particular case I am talking about. So in this particular case, if I plot these two, log 10 T by T sun with log 10 L by L sun, what will I get? I will get a line all the points will lie in this line. Slope of this line is 4. So this expression is exactly, if I'm because I'm plotting the log quantities, this expression is like y equals m, which is 4x, which is log t by t sun, plus c. So this will be just a straight line. So this is one case. The other case, if the radius has no relation T or L of the star, it can have any random value. So in this case, what will I see? L, remember, is now 4 pi sigma. I put a hat over R, that is, this hat is for random, T to the 4. Because that hat is making is random, so if I plot now T versus L, I will get completely scattered points. Okay, I even don't plot in log because I know that it is anyway going to be scattered, so I plot log. Okay, so this is what we understand from our discussion of scattering, from our discussion of correlation. Here you see that T and L are correlated, which happens if all the stars have same radius. And if they don't have same radius and there no relation with L and T, then they will be completely scattered. Okay, so this is why to understand. Now let us look at what happened when people first try to plot these two. Now, as I'm saying that sometimes I'm plotting L versus T, or log 10 of L by L sun versus log 10 of T by T sun, I can also plot sometimes MV versus B minus V if I'm looking at the same cluster. So these are called color magnitude diagrams. But they give you almost the same information. Now, first time these were attempted, it's in 1911. It was attempted by Hertzsprung H and Russell R. Okay. Now, these diagrams are called HR diagram because of this. So they could measure the effective temperature and the luminosity, or on the other way, the color and the B minus V color and the V band magnitude, and then they plotted these diagrams. This is what they saw. So let me tell you a few things about the diagram first here, and then we'll discuss it. So you see, look at the x-axis as plotted in the top part of the diagram, where it says effective temperature. First thing you realize that temperature doesn't increase in the right hand side, it increases in the left hand side. That is how they plotted. In the right hand side, you have the y-axis, which is luminosity compared to sun, which is exactly what I was plotting, L by L sun. And it is in logarithmic scale. Instead of plotting log of L by N sun, the diagram is in logarithmic scale. You see that for unit distance in the diagram, you change by 10 to the 1. That is a very standard choice in certain cases. In the left hand side of the plot, they have plotted the absolute magnitude, and we have said that absolute magnitude and luminosity are very directly related. So that's the absolute magnitude plotted in the left hand side of the plot. In the bottom of the plot, you have something interesting. It talks about spectral class, and you can see O, B, A, F, G, K, M. These spectral classes are kept here with O, S, B0, A0, F0, G0. 0 is corresponds to the subclasses. Now, I will request one of you to look at what is the meaning of spectral classification of stars And that is another way of knowing the effective temperature luminosity of the stars. So I request you to look at that. I will not be able to discuss that in the class here. But it is very important thing in astronomy. So I want one of you to look at it and give a presentation during the class time. We will fix that timing and the person who will look at it in a short while. There is one more thing to look at here is the color of the background which changes with the temperature. So with the high temperature you see blue color, with low temperature you see red color. This is because you remember that the peak of a blackbody spectra, the wavelength at which the peak of a blackbody spectra lies, if I call it lambda max times the temperature remains constant. That's we call Wien's displacement law. So this color is telling you what is the wavelength, which wavelength does the blackbody or the star in this case radiates maximum. Okay. Now let us concentrate on what is being plotted in this diagram. In this diagram is not for a particular cluster if you wish. It can be for all collection of stars where this type of luminosity and temperature measurement has been possible. Okay, so let's see what we have in this diagram. We'll see that most of the stars will lie in this S-shaped region at the center of the diagram, which goes from one corner of the diagram to the other. Even our sun is depicted as one of the stars there. We have Sirius, Regulus, etc., which are some known stars. Proxima Centauri, which is our nearest star, is also there. So most of the stars lies in this strip, and you see, first of all, this strip, if you try to calculate the slope of this strip, again we are not in logarithm versus logarithm plot. Only the y-axis is logarithm, x-axis is not in logarithmic scale. I'm sorry, the x-axis is also in logarithmic scale. You can see the position of 4, 6, 7, 10, and 30. So they are in also logarithmic scale. So it is easier to find the slope from this. So as you see, the x and y both axes are in logarithmic scale. So we can figure out easily that how does the luminosity depends on the temperature. So I request you to find out how the luminosity depends on the temperature and different parts of this strip. And you will agree that it depends differently in different parts of the strip. We also see existence of some regions where there are usually less number of stars called giants. Aldebaran is one of the stars there. And then you have supergiant Betelgeuse is one star over there. And then in the bottom left corner, I have this blue type of patch where I have Sirius B, etc., etc. Okay, so we'll discuss about all of these slowly. So let me plot the HR diagram here schematically. So this is log of temperature with respect to solar temperature with respect to solar luminosity. So if I call it 0 here and 0 here, that will correspond to the sun. So this is my sun. And if you remember, we had this strip where most of the star lies. Because most of the star lie here, we call it main sequence. What about the radius of the main sequence stars? Well, you see, we just discussed if the radius is completely random, this HR diagram will look random, which it does not here, which essentially tells you that the radius either is constant, which you also saw in an example, or it has certain relation with either T or L or both. As you can see, the slope changes at different places. Unlike the slope was constant in this case, we conclude that it is not that the radius is constant. The radius depends on L and or T. It's not L by T, it's L and or T. Okay, what exactly it is, we cannot figure out from looking at the what is the exact dependence. We cannot figure out just looking at this diagram, but this is something that we know that should happen. Now we saw some stars here, and there are two branches. One we call the supergiant, one we call the giants. Let us just consider one branch for the time being. And what does this branch tell you? Now, if I have a star here, let's make it a radar star. So for this star, what about the radius? So what is the radius of this star? If it would have lied in the main sequence, its radius could have been there, right? Now I can calculate the radius of any star in the following way. Just inverting this relation, it will be L by 4 pi sigma T to the 4. So that will give me the radius, right? For this star, L is more than what it could be if it was in the main sequence. What does it tell you? It tells you that the radius of this red star is greater than the radius of the same star in the main sequence. So we call this, because of that, we call it giant. So these stars, because of this fact, are called red giants. Why it is called red, we will understand a little later in the course, but you understand now why they are called giants. If I now look at another star over here, and remember that there was a population of stars which are lying there. So let us ask the question, what happens to this star which is lying there? And again, now I don't need to go through the argument once more, but we will agree that for this L is less than what would be the L in main sequence, and this is for the same temperature. So this tells you that this star has a radius which is lesser than the radius that it could have been of the same temperature in the main sequence. So these are called dwarfs. Small, so dwarfs, big, so giants. So red giants are giants and dwarfs. Okay, and this is for the main sequence. So we learned two things here, that R is not completely random. It depends on the L by T, and or T. There are stars which are not in the main sequence. So for these stars, giants and dwarfs, they must be something different from all the other stars that we have here. This is what I can tell you just looking at all the stars in this HR diagram. So remember, this is what I call the HR diagram. Now, in the introductory lecture, we said that we know that there are two types of star clusters. One we call the open cluster, and the other we call the globular clusters. Okay. Now it is interesting to look at the HR diagrams for this open or globular cluster because of two reasons. One is that the star clusters are gravitationally bound object. So they must have been created from the same initial cloud, or they should have some same initial composition. They're created from the same cloud and they stay gravitationally bound for some time. So they should be in the same initial composition. Their initial composition should be same. Open clusters or the globular cluster, if I want to look at the HR diagram for these, I don't need to calibrate the y-axis that much, because what will happen if I don't calibrate the y-axis is that position of the 0 in the y-axis will just change, go up and down. But all these stars, so this characteristic picture will just move up and down in the y-axis if I don't calibrate for the distance to the cluster. So even if I do not know the distance to the cluster and comparing and plotting the HR diagram for all the stars in a given cluster, then I don't care that much. Now for an open cluster, remember that these are relatively newer and these are relatively older, and that we know just looking at them, because the open clusters are, the shape of the open cluster is more like a random shape, while the globular clusters are more spheroidal shape. And we argued that anything you keep in gravity for a long time, it will attain a spheroidal shape. So when one looks at the star clusters, and this is for the open cluster, like Pleiades if you wish. So this is log 10 T by T sun, and then again so I'm writing L by L sun here, but it's not necessarily calibrated this way. So here you see the main sequence mostly, and very little giants and extremely little dwarfs. So there is almost no giant and hardly there is any dwarf. Okay. And when I look at a globular cluster, the HR diagram, old population of star, we see something completely remarkably different. The tail part here remains the same, Here we see that there is a pathway. Okay. So the top part of the HR diagram. So the top part corresponds to, remember, the temperature increasing this way. These are the, or let me level it in the previous diagram itself. So these are high temperature and luminosity, and these are low temperature and low luminosity. The stars have low temperature and low luminosity, high temperature and high luminosity. And what we observe is that the high temperature and luminosity stars has disappeared. There are a lot of giants and some quite a bit of dwarfs, and there is no high temperature or luminosity star. Okay, and there is a bridge being created between the part where the giants lies and the main sequence. The top part of the main sequence is depleted, and if you see an intermediate, so now as you can see that there is an evolution between here to here. There is a time evolution. So the stars do evolve, because when I look at open cluster, I look at the newer stars, their HR diagram is different from the HR diagram of the globular cluster where I have older stars. So there is time evolution. And now, because we know this, and once we learn the stellar structure, we'll see how the time evolution happens roughly, not in very detail. But as you go to some intermediate time, go to a cluster which has edge which is intermediate between these two, you will see the HR diagram looking like this, where in, from the left to the right, the top part of the HR diagram gets depleted, and there is more giants that comes in and more dwarfs comes in. Okay, so there is a time evolution of the stellar of the stars. So this is what we know from here. We also realize that in the right hand side, where I have the stars, the population of stars has evolved more. There is no high temperature and luminosity star, which essentially means that the stars which has high temperature and luminosity does not live for longer. If they would have lived by the same amount of the low temperature and luminosity stars, they would have been present in the right hand part, but they doesn't live longer. Because of that, this has happened. All right, now there is one more observation which is more recent than Hertzsprung and Russell, and that is because this requires the measurement of the mass of the star. Now, how you can measure the mass of a star? You can measure the mass of a star if the star is in binary, because you know the time period and the mass are related by Kepler's third law. So measurement of stars mass for binaries. Binaries means when two stars are going around each other. I remember that we took one example in the introductory class where we talked about the miser and Alker, and miser and miser A, I think we looked at, which was a binary star. Now for these stars, you can measure the mass. And if I measure the mass, and then again, I can obviously, we have said that we can measure the luminosity already. So we measure the mass and luminosity, and we plot a diagram which is not quite the HR diagram, but a similar scattering plot diagram, scatter plot diagram, which is this. Now again, if mass and luminosity are completely uncorrelated, they doesn't depend on each other at all, then I will expect this to be a complete scatter plot. The points will be anywhere. But when you plot, so let me also level this. So when you plot, so obviously this will be our sun. You see that this I am plotting by hand, so it may not be exact, but this is the kind of relation that you see. So it's kind of piecewise straight line or piecewise logarithmic. So if I say L by L star equals will be some m by m star to the power some number nu, such that if I plot log of, so if I now plot log of L by L star, that will be nu times log of m by m star. And you see that nu will be the slope of the curve that I have drawn in the right hand side. And it's found that at the high mass range, so this is log 10, so it is like, if you wish, 200 times solar mass. That much massive stars are not found, but maybe 30-40 times solar mass range. This nu is 3. In the region here, this is 4.5, and for the subsolar mass stars, it is 2.5. Okay, so now we realize a few things. We realize that L, M, T are all related, even radius. We realize that there is an evolution. This curve is also telling you larger luminosity corresponds to larger mass, which means we found from here that the large luminosity stars live less, so we can conclude that large mass stars. So these things were known just from the observations. Well, I should not say just from the observations, because that is quite complicated, but this was known. And let me give you a very rough estimate of what is the range of these quantities we are looking at. Again, it's a very rough estimate because these numbers are not quite accurate, but still, let me give you some idea. So what I'll do is, I will plot the minimum and maximum numbers observed for the quantities like log 10 of luminosity with respect to solar luminosity, mass with respect to solar mass, temperature with respect to solar temperature. Solar temperature is, so solar luminosity, solar mass, solar temperature, and solar radius. Please look at these numbers. These are very, very sacrosanct number in stellar astrophysics. Please look at this number and fill up this 100th time of the luminosity of the sun to 10 to the 4th times the luminosity of the sun. 1/10 of the solar mass to 10 to 30-40 times. I think 100 solar mass is also observed nowadays, but it's more likely to be within 10, most of the stars. Half solar temperature, which is 6,000. So now one need to develop a theory to explain this understanding. So we do have observed something but it is not good enough to understand everything about the star. So we need to proceed to make a theory. And so let's start that and then we'll carry it forward from there in the next discussion. So we talk about modeling a star. First question is what we are going to model. So what is a star? It's a gravitationally bound object that emits its own radiation. So it has an energy source inside. I guess that all of you know that energy source is because of fusion. So now when you start a model, you start with some assumptions and you justify the assumptions also. So what are our assumptions for this model? Let us go through the assumptions. First is, I call it isolation. Most of the stars are isolated. So for example, now I have to write the radius of the sun is around 7 into 10 to the 8 meter. Now the distance to the nearest distance to Proxima Centauri is about 1 parsec, which from the last quiz you know is 3 into 10 to the 16 meter. So you see that the distance to the nearest star is humongously large compared to the radius of the star. So if I am looking at a collection of stars, each star is just a dust, a speck in that. No influence or anything external in the star. So that's a very good assumption. Okay. Now it is not always true, obviously. There are the planets which influences a little bit, but it's very tiny amount. And then there can be those binary stars where it goes around each other. So when you talk about things like gravitational kinetic energy, you have to take care of the energy of the other star. But those are more complicated objects which we are not dealing with here. So we deal with most of the stars which lives in isolation. Composition. Most of the star is almost hydrogen. 70% of it is hydrogen. 70% by mass. And the rest 30% is helium. Now obviously the stars has many other elements, but they are almost not there. For example, if we have sun, for the sun if I have 10,000 hydrogen atoms, I'll have 8 oxygen atoms and 4 carbon atoms. So for the compositional purpose where I may have to calculate the number of certain elements with respect to the mass from the mass where I, so if I say what is the number of hydrogen atom, how will I calculate that? The number of hydrogen atom will be mass in the hydrogen atom divided by mass of each hydrogen atom. And if I want to do this, so now I know that this is 70%, so I can just calculate it this way. I don't need to bother about the oxygens and carbons because to the first precision to the manyth precision they are not there. Okay, so that is about the composition. We'll talk about composition again in a short while. Now, when we talk about or compare the stars in a cluster, the composition of all stars, and this is more true for an open cluster. In an open cluster is same. Okay, that is an assumption that we are going to take. The composition is same for all these stars. It's not quite true if you are looking at a older cluster, but for a newer cluster it is almost always true because they are formed from the same interstellar cloud. We'll assume spherical symmetry. That is, that the star is a sphere of radius r, and everything that changes with this radius. Now you may say that okay, so there is this rotation, and the rotation, just like for the earth, we know bulges up the equator of the earth a little bit. So if you calculate, say for rotation, how much is the effect of rotation in the spherical symmetry of the star? So I say rotational kinetic energy by gravitational potential energy. Okay. Now, when I'm doing this calculation, I'm just trying to do an order of magnitude estimate, so I don't need to be very precise. So this, if you want to put in, so this is mv square. V for rotation is omega times r. I even forget about that half here. And this is gm square by r. And then there can be factors which I again forget. And if you calculate this for the sun, it will be 10 to the minus 5. So the rotational kinetic energy is 10 to the minus 5 times the gravitational potential energy. Gravitational potential energy is spherically symmetric, so it will try to keep the stars as a sphere, and it will stay as a sphere. The rotation will not have much effect. What about magnetic field? So the magnetic field also lines up things in a certain direction, which will destroy the rotational symmetry. So if you calculate now the energy in magnetic field by the gravitational potential energy, this turns out to be even smaller. It's much smaller, 10 to the minus 11. So I can forget about that. So we can assume spherical symmetry easily. Next assumption going to be is the star is in local thermodynamic equilibrium. So what does it mean? It means that if I think of now my spherical star, the temperature will be different at the center and in the core. So there will be a change in temperature with radius. But locally, if I consider a small region here, the temperature remains same, or the temperature can be defined. If you consider ideal gas law, which is quite applicable for a star like Sun, so I have P equals rho k T by m. M is the mass of individual molecules or atoms here, and though we said that the composition has helium and hydrogen, many cases we will see that I will just put the mass of hydrogen here, neglecting the helium. So that will make us wrong by a few factors, but we will tolerate such wrong things for some time. Now you can imagine the pressure at surface, that is at smaller equals capital R. R is the obvious choice of the origin, is at the center of the star, and R increases from the origin. So in R equals to R, the pressure P at R, it must be 0, because otherwise either it will compress the star or it will evaporate things from the surface of the star. I'm not saying it does not happen, but that effect is extremely small. The pressure can be considered as 0. At the center, the pressure should be enormous because the entire star is pushing inwards with gravity. So the pressure varies as a function of R. And the density, obviously, it varies as a function of R. So T also varies as a function of R. So T, which is the temperature, can be defined and can be defined locally. Now you may ask the question, you should ask the question, how do how is it that locally there is a temperature established? That is because the opacity inside is extremely high. And we know that if if the opacity or the optical depth is very high, we can define a temperature. Okay. Now you will see over shorter time scale, luminosity, temperature, radius of the star of a star, shorter means can be few days, seen to vary. Okay, so it is observed that these quantities vary in a time scale of days, which means I cannot parameterize my star in terms of any of these quantities. On the other hand, the star is isolated. That is my first assumption. This tells me that m is a constant, mass is a constant, mass of the star. Now it is not that in the entire journey of the star the mass remains constant, but most of the journey of the star which we'll deal with, the mass remains constant. So because of that, we'll use mass to parameterize the star. Even when you try to write down the differential equations, say the radius changes. So if I consider a shell at radius r and r plus dr, within r and r plus dr, because the radius of the star can change, so they say the entire star is like expanding like a balloon, then I cannot ask the question that what is this area and what is happening to this area, because there is a time change that will come into picture. So what we do is, we know that the mass inside this region can be written as spherically symmetric, so 4 pi r square rho in that region times dr. So often we parameterize the star. Instead of writing a derivative with respect to radius, sometimes we write a derivative with respect to the mass. When we say that this mass element which is in this shell, it may go out or come in, the entire shell may go out and come in because of the star is oscillating, the radius of the star is changing, but the mass inside that remains the same. So that is why we will write it as, instead of taking derivative with respect to r, we may take derivative with respect to m. So with all of this, we come up with this model where we are asking the question now that what are the quantities we will seek change for and what are the type of changes that we'll seek for. It's quantities. So one is the density of the star, which I can write either as a function of mass and time or as a function of radius and time. As we said, we can go from radius to mass using this expression. The other is the temperature. And as we said, that if we know the density and temperature, then we can know the pressure. So I don't need to write an expression for the pressure separately. It's already there once we know the density and temperature. And then I have compositions. Like if I consider the ith element, I call something called xi, which is a function of m and t again. What this is the mass of the ith element by the total mass. And again, this can be either written in terms of mt or nt, or sorry, mt or rt. And there can be, for the compositions, there can be some n elements in general. So what we have is, we have n plus 2 variables to solve for all time and all radius. There is one catch here. So if I have n plus 1 compositional elements, then I have n plus 2 here, because if you look at xi, so if I add all of xi, should be 1. So that is a constraint. So I have n plus 2 variables to solve for. Okay, so I'll stop here today. It was a little bit extended today, but I don't think that we discussed a lot of complicated things. She should be fine.